Imagine a construction site where a building does not rise slowly floor by floor over several years. Imagine that instead of mountains of concrete, scaffolding, and thousands of workers, the building seems to assemble itself, almost like a giant industrial machine putting together its own parts. Massive sections arrive from a factory, already containing much of their structure and internal systems. Cranes lift them into place with extraordinary precision. Workers connect them together, and within a surprisingly short period, a structure that would normally take months or years begins transforming the skyline. That may sound like science fiction, but versions of this construction method are already being used in China. Companies there have spent years experimenting with a radically different approach to building cities. Instead of treating every construction project as a unique operation built entirely on location, these companies move a large part of the process into factories. Building components are manufactured under controlled conditions, then transported to the site for rapid assembly. People often compare it to Lego. A 30-story building is obviously not made from toy bricks. The engineering required to make a high-rise safe, stable, and durable is far more complex than stacking one box on another. But the comparison is useful because the philosophy is similar. Instead of creating every piece on site, engineers design standardized sections that can be manufactured in advance, transported to their destination, and connected together as part of a larger structural system. China's Broad Group became internationally famous for demonstrating how dramatic this approach can look. Its projects include a 30-story tower, the T30, assembled in 15 days, and the 57-story mini-sky city in Changsha, erected in 19 days using a heavily prefabricated steel system. But a key detail is often lost in the viral headlines. Those extraordinary assembly times did not mean the entire project, including factory manufacturing, foundations, approvals, and finishing, happened within those few days. Much of the work was already complete before the rapid on-site assembly began. That distinction may actually make the technology more interesting, because the real revolution is not about building a skyscraper overnight. It is about changing the answer to a more fundamental question. Where should a building actually be built? For more than a century, the basic logic of construction has stayed familiar. Workers, materials, machinery, and equipment are brought to a piece of land and the building takes shape there. Concrete is poured, steel is installed, walls go up. Electrical systems are connected, plumbing is added. Each stage depends on the one before it. The process works. It has produced some of the most extraordinary buildings in human history, but it has a major weakness. Construction sites are extremely difficult to control. Weather changes constantly, materials arrive late, workers from different trades must coordinate. A small mistake can create delays further down the project. Equipment has to move around a constantly changing environment, and much of the work happens outdoors, in conditions no factory manager would choose for precision manufacturing. A factory operates differently. The environment is controlled. Equipment stays in fixed locations. Workers specialize in particular tasks. Materials arrive on predictable schedules. Quality checks repeat systematically. Production follows the same sequence over and over. That difference is at the heart of China's experiment. Instead of bringing the entire manufacturing process to the building site, the idea is to manufacture as much of the building as possible elsewhere and turn the construction site into a place where completed or partially completed sections are simply assembled. Think about how a car is made. Nobody sends raw steel, loose wires, and glass to a parking lot and asks workers to build a car from scratch outdoors. Manufacturing became efficient because factories learned to standardize components, organize production lines, and repeat optimized processes thousands or millions of times. Modular construction applies that same thinking to buildings. A section can be designed digitally before entering production. Steel frames are manufactured to precise dimensions. Pipes and electrical systems are integrated before the module leaves the factory. Flooring, walls, and windows can be installed in advance. When the finished section arrives at the site, workers are not starting with raw materials. They are receiving something already close to a finished part of the building. The crane lifts it into position. The structural connections are secured. Electrical and mechanical systems are connected. Then the next section arrives. And another. This is why the visual effect can be so dramatic. What looks like a building rising at impossible speed is often the final stage of a much longer manufacturing process that began somewhere else. Broad, Sustainable Building has described its system as relying heavily on factory production, with standardized components manufactured in advance and shipped to the site for assembly. The company says its Mini Sky City project used a system that was roughly 90% prefabricated. That sounds simple until you consider what it takes to make a high-rise actually work. A tall building is not a collection of stacked rooms. Every floor transfers load through the structure below it. Columns, beams, and connections must function as a single system. The building has to withstand wind forces that increase at higher elevations. In seismic regions, it must also satisfy demanding earthquake requirements. Fire protection has to work across the whole structure, and plumbing, ventilation, and wiring must connect reliably between sections. And there is another challenge: precision. When you assemble a 30-story building from standardized components, small inaccuracies can compound into serious problems. A connection slightly out of alignment on one level can create a much larger issue several floors up. The modules cannot just be manufactured quickly. They have to be manufactured consistently. This is where factory production offers an advantage. In a controlled environment, engineers can establish repeatable processes and inspect components before they ever leave the facility. Materials are measured and cut with precise machinery. Workers repeat specialized tasks. Defects can be caught before a component reaches the site. But modular construction also creates a challenge traditional construction does not face to the same degree: transportation. A massive module may be easy to build inside a factory, but once it is finished, someone has to move it through the real world. It has to travel highways. It has to pass through intersections, under bridges, around existing infrastructure. Road dimensions matter. Weight limits matter. Traffic matters. A module too large for the transportation network becomes an engineering problem before it even reaches the site. This means modular construction is not only a construction technology, it is also a logistics technology. The factory, the transportation system, and the construction site all have to operate as parts of a single coordinated process. If the factory produces modules faster than they can be delivered, storage becomes a problem. If trucks arrive late, cranes and workers wait. If modules arrive out of sequence, the entire assembly schedule can be disrupted. The faster the construction process becomes, the more important coordination becomes. That is one reason copying a viral construction project elsewhere is much harder than it looks. The speed of the final assembly depends on everything that happened before the first crane started lifting. The building has to be designed around the system. The components have to be manufactured. The foundations have to be prepared. The transportation network has to handle the deliveries. The assembly sequence has to be planned in advance. And the connections between modules have to work exactly as intended. When all of that is in place, the visible construction stage can move at extraordinary speed. Broad's 57-story mini-sky city is one of the most famous examples. It was erected in Changsha in 19 days, at a reported pace of roughly 3 floors per day, with about 90% of the building manufactured off-site before assembly. The completed project contains apartments and office space, showing the system was meant for a functioning building, not just a demonstration. The 30-story T30 project shows the same principle. It was assembled in roughly 15 days, although the broader project timeline included work completed before that rapid erection period began. This is where many viral videos become misleading. A headline reading, "China builds a 30-story building in 15 days," creates an incredible sense of speed. But it can also give the false impression that workers started with an empty field and finished a building 15 days later. That is not what happened. The factory manufacturing, substructure work, planning, and engineering existed outside the spectacular phase captured in the time-lapse videos, but this does not make the achievement less impressive. In some ways, it makes it more significant. Because moving work away from the construction site is exactly what allows the assembly process to move so fast. The building is not appearing from nowhere. It is arriving at the site in an advanced state of completion. The construction industry has historically been built around sequential work. One stage often has to finish before the next begins. The foundation has to be ready before the structure rises. Structural work must reach certain stages before interior systems go in. Contractors have to coordinate carefully. Delays spread from one stage to another. Modular construction changes part of that sequence by letting different stages happen in parallel. While workers prepare the site, a factory can manufacture structural sections. While one part of the building is assembled, additional modules can be completed elsewhere. Instead of waiting for every previous stage to finish, multiple parts of the project progress simultaneously. Parallel work is one of the most powerful ways to shorten a project timeline. Imagine a section that normally takes 6 months to build on site. Now imagine the site needs 2 months of foundation work, while the factory simultaneously spends several months manufacturing the structural modules. When the foundation is ready, the factory-built sections may also be ready for delivery. The project has overlapped tasks that would normally happen one after another. The total work has not disappeared. It has been reorganized. That may be the most important lesson behind China's Lego-style buildings. The future of construction may not depend on workers becoming dramatically faster at the same jobs. It may depend on changing the entire workflow so the construction site no longer performs every task. Some tasks belong in a factory, others belong on site. The goal is figuring out which activities can be standardized and repeated, and which require adaptation to a specific location. This creates another advantage: predictability. Traditional projects face enormous variables. Rain delays concrete work. Extreme temperatures affect schedules. Material shortages disrupt projects. A missing component delays an installation. Conflicting schedules and design problems discovered mid-construction force costly changes. A factory cannot eliminate every risk, but it can control far more of them. The same environment is used every day. Equipment stays in fixed locations. Workers develop specialized skills. Materials are inspected systematically. The same assembly sequence can be refined over time. This is why modular construction could eventually matter more than simply building one skyscraper quickly. The deeper question is whether buildings can become products. Not identical cities, but products in the sense that large portions of construction could be standardized, manufactured, and repeatedly improved through industrial processes. A developer could choose from standardized structural systems. A factory could manufacture the required components. Digital systems could track each component from production through transportation to installation. The building could be assembled using a carefully planned sequence. Sensors could monitor the structure throughout its lifetime. That would create a very different construction system. But it introduces an enormous challenge. Buildings are not cars. A car factory produces thousands of nearly identical vehicles. A building must exist on a specific piece of land in a specific climate, under specific regulations, with specific architecture and specific geology. One city faces earthquakes, another faces hurricanes, another faces extreme snow loads. One site has strong bedrock near the surface, another needs extensive foundation engineering. Construction can never become completely standardized. The challenge is finding the right balance. Too much customization destroys the economic advantages of mass production. Too much standardization makes the final product unsuitable for real-world needs. The most successful modular systems need to standardize what can be repeated while preserving enough flexibility to adapt. That is much harder than simply designing a large, rectangular module. The structural system needs standardized connections. Mechanical and electrical systems need reliable interfaces. Dimensions need to be consistent enough for efficient manufacturing and transport. At the same time, architects and developers still want different layouts, different exteriors, and different internal configurations. The future may therefore look less like every building being identical and more like modern technology platforms, a standardized structural platform underneath multiple different building designs. The underlying engineering repeats while the finished buildings still look different. China's broader prefabricated construction industry has been developing around this kind of approach, connecting digital design, manufacturing, construction, and project management more closely than traditional methods allow. Broadhomes, for example, describes integrating design, manufacturing, and construction through digital systems and large-scale prefabricated production. And the implications could extend far beyond skyscrapers. Think about housing. Cities worldwide face shortages while construction projects take years. A more industrialized approach could speed up delivery of standardized residential buildings, especially when large numbers of similar apartments are needed. Think about hospitals. They contain highly repetitive systems, rooms, mechanical infrastructure, technical equipment that could be manufactured under controlled conditions and assembled as part of a larger project. Think about hotels. Rooms are often repeated hundreds of times within a single building, which a modular process could take full advantage of. Think about schools. Standardized classrooms could be manufactured more efficiently when the same components repeat. And think about disaster recovery. After an earthquake, hurricane, or other disaster, communities may need large numbers of buildings quickly. A manufacturing-based system could produce standardized modules away from the damaged area and transport them where needed. The possibilities are enormous. But modular construction has a major economic problem. Factories are expensive. A company cannot build a massive manufacturing facility, employ thousands of workers, and install advanced equipment without a reliable pipeline of projects. Economics improve when the factory produces large numbers of modules because fixed costs spread across greater volume. This means scale matters. A factory producing modules for one small project may not be efficient. A factory producing thousands of standardized components for dozens or hundreds of projects could achieve very different economics. And this creates a feedback loop. As more buildings use the same system, manufacturers improve their processes. Workers gain experience, suppliers specialize, equipment gets optimized, defects get identified earlier, digital models improve. The next generation of buildings benefits from what was learned on the last one. Traditional construction has always learned from previous projects, but modular manufacturing could make that learning far more systematic. A company might discover a connection takes too long to install. The next generation of the system redesigns it. A transportation problem might reveal modules are too large for certain roads. Future designs adjust. A component might repeatedly fail inspection. The factory modifies the production process. This is exactly how manufacturing industries improve. The factory becomes a learning system. Once construction operates more like manufacturing, the industry could start collecting and using data in ways that were previously much harder to implement. Artificial intelligence could make that system even more powerful. Before construction begins, software could analyze thousands of design possibilities, identify the most efficient combination of modules, estimate material requirements, simulate transportation routes, calculate assembly sequences, and flag potential bottlenecks before a single component enters production. A digital model of the building could follow the project from design to manufacturing. The factory would know exactly which components are required. The transportation system could track their location. The construction team would know when each module is expected to arrive. And once the building is complete, the same digital information could be used for maintenance and future renovations. This concept is often called a digital twin. Instead of just drawings, the owner has a continuously updated digital model connected to the real structure. But even the most advanced digital system cannot escape the basic realities of engineering. Gravity still exists, wind still exists, earthquakes still exist, fire safety still matters. And the faster a building is assembled, the more important it becomes that speed does not compromise safety. This is why one of the biggest mistakes people make when discussing China's rapid construction is focusing only on the stopwatch. Speed is impressive, but speed is not the same as quality. The real question is whether a construction system can repeatedly produce structures that meet demanding safety and performance requirements, while we're also reducing time, cost, and environmental impact. A building assembled in 5 days but needing major repairs a few years later would not represent a successful revolution. A building assembled rapidly but unable to meet safety requirements would be even worse. The real goal is not simply to build faster, it is to build better systems. Stronger quality control, reliable structural connections, predictable manufacturing, efficient transportation, and careful inspection at every stage. Broad's more recent modular work shows the company continuing to push rapid assembly further. In 2024, an industry report described the assembly of a 26-story residential tower over 5 days using the company's modular hold-on system, again showing how quickly the visible construction phase can move when the structure is designed around prefabricated components. But the broader future of modular construction will not be decided by one company or one viral video. It depends on solving several difficult problems. Can modular buildings compete economically with traditional construction? Can factories operate efficiently enough to justify their enormous upfront costs? Can transportation networks support increasingly large modules? Can standardized systems stay flexible enough for different cities and projects? Can regulators and building codes adapt to new technologies while maintaining strict safety standards? And perhaps most importantly, will developers, architects, and customers trust these buildings? Public perception matters. For many years, prefabricated construction was associated with cheap, temporary, or low-quality buildings. Changing that perception requires proving that factory-built structures can be durable, attractive, and appropriate for everything from housing to high-rises. The technology itself may already be ready. The market may still need convincing. This is one reason spectacular projects are so valuable. When a company assembles a 57-story building in 19 days, it creates a powerful demonstration of what the technology can do. Even skeptics are forced to confront the underlying possibility. What if construction does not have to happen entirely at the construction site? What if a skyscraper can be largely manufactured before the public ever sees it? What if the visible process of building a city could become dramatically faster because most of the real work happened somewhere else? Those questions matter more than the viral video itself. Because construction is one of the largest industries on Earth. Cities are still growing. Millions of new homes are needed. Infrastructure is aging. Labor shortages are becoming a serious concern in many countries. And governments face increasing pressure to reduce the environmental impact of construction. If industrialized construction can solve even part of these problems, the impact could be enormous. The future will not be a world where every building is assembled from giant boxes. Traditional construction will continue because many projects are too unique, too complex, or too location-specific for full standardization. Historic buildings will require specialized restoration. Irregular architecture will require custom engineering. Dense urban projects will face complicated site conditions. Some buildings will simply be too unique for a factory-based system. But modular construction does not need to replace everything. It only needs to become better at the applications where repetition, speed, and standardization create a meaningful advantage. Apartment buildings, hotels, hospitals, schools, data centers, commercial buildings, affordable housing, and potentially entire urban developments designed around standardized systems. That is where China's experiments could become globally important. The country is not simply building buildings quickly. It is testing whether the entire process of creating a building can be reorganized. For centuries, humans have brought factories to the building site. The materials arrive, the workers arrive, the machinery arrives, and the building is gradually manufactured outdoors. Modular construction begins reversing that relationship. Instead of bringing the factory to the building, it brings the building into the factory. Then, once enough of the structure is complete, the finished sections travel to their final destination. The construction site becomes the last stage of a much larger industrial process. And when you think about it that way, the Lego comparison starts to make more sense. The modules are not the entire story. The real story is the system behind them: the digital design, the manufacturing process, the supply chain, the transportation network, the crane operations, the structural connections, the quality control systems, and the carefully planned sequence that gets thousands of components to the right place at exactly the right time. A 30-story building may appear to rise in a matter of days, but that speed is only possible because months or years of engineering, manufacturing, and planning were compressed into a process that began long before the first module was ever lifted. That is the real secret. China has not discovered a way to eliminate construction. It is discovering ways to move construction from the unpredictable environment of the building site into the controlled environment of the factory, from sequential work into parallel production, from individual projects into repeatable systems. And if that transformation continues, the skyline of the future may begin somewhere most people never see. Not on a construction site, not beneath a giant crane, but inside a factory where the walls, floors, columns, and electrical systems of tomorrow's buildings are already being manufactured long before the first visible floor appears above the ground. The first module arrives. The crane lifts it into position. Workers secure the connections. Another module follows, then another. And eventually, what looked like an empty construction site becomes a building. Not because the laws of physics changed, not because engineers discovered a magical shortcut, but because they changed the process. And sometimes, changing the process is more powerful than simply trying to work faster. The future of construction may not be about building cities the way we always have, only faster. It may be about realizing that a city itself can become part of a manufacturing system. A system where buildings are designed digitally, produced with industrial precision, transported through coordinated supply chains, and assembled at remarkable speed. China's Lego-style high-rises may therefore be much more than an impressive construction trick. They could represent an early glimpse of a much larger transformation. Because the next time you watch a skyscraper rise floor by floor in a matter of days, the most important question may not be how quickly the crane is moving. The real question may be this: how much of that building was already finished before construction appeared to begin? And if more and more of our buildings can be manufactured before they reach the construction site, then the cities of the future may not simply be built faster. They may be built in an entirely different way.